inspired neuromorphic processing. After earning bachelor's and master's degree in computer science, Sir worked in the software industry before joining Newcastle University, UK, where he worked as a lead researcher in several UK e-science projects, contributing to the development of W3C standards for web services and the concept of cloud. With a PhD in grid computing, he returned to Kolkata, worked in a telecommunications revenue assurance product company for 3 years before joining TCS Research in 2011. Sir currently leads research in edge and neuromorphic systems. A distinguished scientist, awardee at TCS Research, Arijit Sir has more than 75 publications, more than 50 patents, and a Google Scholar H index of 20. With this introduction, I would like to request Sir to start your session. Sir, Arijit Sir, over to you.
Yeah, thank you and welcome to this first session. I hope you can hear me properly and also see the screen.
Yes, sir, absolutely.
Okay, fine. So this advanced computing in the sense is a very broad topic. So I'll just point out few things that we think is going to be the future of computing, and from then on I'll on low power computing using neuromorphic systems. So the face of computing has changed dramatically over the past 20 years or so. So if you remember, by 2007-8, the first idea of cloud came about. So earlier, before that, all computing resources were local. You had labs, you had huge machines in the labs, and you worked on those machines. What Amazon did was Amazon introduced their the elastic computing cloud back in 2008, 7, 8, something like that. And that changed the whole face of computing by allowing access to almost infinite computing resources. Almost at the same time, the face of data changed dramatically as well. So Facebooks and MySpaces and all those things started appearing. So you had huge volume of data available for experimenting with different things. So neural networks kind of got a new life at that point of time. So we started having more powerful computers, more data for processing, for analysis. So the face of applications also changed. So there were more demanding applications and new use cases. Things like if you consider the healthcare sensors related to healthcare. So human body, we have sensors all around us, things like our smartphones, our smart watches and smart bands, smart rings, all these things, they are each of these things are connected. There are currently around more than 100 billion sensors that are connected. So using these sensors, people started dreaming about sophisticated healthcare applications that will monitor the body vitals of patients and take necessary action. So for example, you can think of in old age homes, people live alone. Elder people live alone. Now they're not very confident about having cameras inside the homes because camera is a privacy issue. So if you can think of people, so one such elderly couple, for example, they have smart watches and other healthcare sensors on their bodies. Those sensors measure their heart rate, their pulse rate, their ECGs, and all sorts of things, body temperatures, and all those things. Now imagine one such person in the middle of the night wakes up and goes to the bathroom, turns on the tap, and at that point of time he suffers a stroke. Earlier if you don't have these sensors, so I mean somebody will have to figure out what happened to the person. He might have become unconscious inside the bathroom won't be able to call anybody. So that was scary. So now if you have all these sensors connected to a human body, from the heart rate monitors, you can figure out that there is something wrong with his heart rate. Maybe the heart rate is irregular. The accelerometer fitted with the smartwatch denotes that the person has fallen down. The PIR sensors inside the room denotes that the person has gone to the bathroom, and some moisture sensor may also denote that he has opened the tap. So combining all these things together, it can deduce that the elderly person has gone to the bathroom, opened the tap, and there is some problem there because his heart rate is irregular and he has fallen down. So if all these things can be analyzed inside the premises using all these sensors and other devices that are there inside the house, inside the home, you can send a 911 signal, a call to the hospital or the healthcare provider. So these are some types of applications that people started dreaming about. The future of automobiles is also some example that we can talk about. So you know about the autonomous vehicles, Tesla and all. They are building autonomous vehicles. Now, autonomous vehicles is just a start. The future of automobiles from 5 to 10 years from now on is software defined vehicles, where a vehicle is actually like your mobile phone. You download any kind of application from Google Play Store or Apple's App Store. A car will also be something like this. You will be able to download various kind of applications on the car, not just the infotainment system, but also other kind of applications. Sorry, I'm hearing some noises. I'm audible, right? Okay. Shall I continue?
Yes, please.
Okay. So software defined vehicles means that your car is almost, I mean, you can download applications, different types of applications, even for the functionality of the car. For example, you bought a Maruti, you like the infotainment system of BMW, you can exchange that. You can download that infotainment system that will run on your car. Obviously, there are checks to be made whether that new application that you are downloading is compatible to your car, whether it's security verified, and all those safety critical things, whether they are safe or not. All those things have to be done. But the car will be defined like a mobile phone. Like you customize your mobile phone, you will also be able to customize your car. That is the future of vehicles, of automobiles. So all these things are changing the entire spectrum of computing. And by advanced computing, we mean this umbrella of different things that are going to happen. So when the spectrum of computing is changing, at the same time, heterogeneity is also increasing. I mean, there's a huge heterogeneity among the computing infrastructure today, and that is also going to increase in future. So you have these nowadays, you have the current general purpose computing systems that are, say, for example, CPUs, GPUs, FPGAs, TPUs, or tensor processing units. That is the current spectrum. There are evolving computing systems or infrastructures that are tailor made for certain domains. So neuromorphic, quantum, in-memory computing, all these things are evolving for maybe the last 4 or 5 years, and they're reaching a stage of maturity, probably will be mature in the next 3-4 years. Then you have the potential to redefine the computing paradigm with further disruptive technologies, biocomputing, photonic computing, molecular computing, that is going to disrupt the entire future spectrum of computing. So the current technologies form the backbone. And on top of that, you have these emerging architectures that address specific domains and specific challenges. And then the future paradigms that might evolve. The researches are going on in all those areas that will evolve to promise unprecedented innovation. So this is the spectrum of heterogeneity. Now, if you want to navigate through these heterogeneous computing systems, you have your CPUs, GPUs, TPUs, FPGAs, then you have the neuromorphic quantum, all those things coming in. Then at some point of time, you'll have photonic and all other different forms coming in. So how do you deal with these heterogeneity? So any computing system, rather any system actually, even if it's a building for civil engineers or cars designed by mechanical or automobile engineers, the concept is same. You first design something where you actually assess the hardware compatibility, the performance for which you need simulations and emulations to be done. So that is the design phase. Then you have the build phase where you are actually building something. And this is the phase, this build phase, where this heterogeneity becomes a headache. So you have different types of infrastructure. Many of them are not compatible with each other. So there is an issue with portability across all these diverse type of hardware. So you might have to design a middleware for software-defined vehicles that will make all these applications that I was talking about, like the Google Play Store, there will be a automobile app store. That this middleware will make sure that all those applications are portable across different types of ECUs, not just the Tesla ECU, maybe the Honda ECU or the ECU coming from Volkswagen. They'll make sure that the applications are portable. So that middleware, this is the target of the build phase. And then comes the run phase, when you actually execute the things. There you have to efficiently distribute the workload of different types of tasks that are happening together. You have to schedule them, you have to maintain the workload, you have to maintain the safety, security, and all those things. So for example, I have listed a few. So you can use GPUs for navigation, you can use neuromorphic systems for real-time decision making. So all these things happen in the run phase. So you practically have to venture through this design, build, and run phase for any kind of workload or any kind of task that will come in for the future heterogeneous hardware or heterogeneous connected systems. Now, at the same time, we are also seeing a transition towards the edge. So cloud was there. We did a lot of things with the cloud. Even now we are doing a lot of things with the cloud, but edge is becoming more and more important for some kind of some specific type of applications, especially where you need extreme low latency, where your round trip time required to send the data to the cloud, get it processed there and get the answer back, that is not allowed. For example, I can tell you about tractors in precision agriculture that are evolving now, where they have a small camera systems fitted underneath the tractors. The tractor is moving, at the same time the camera is trying to detect whether there are weeds in the field or not. If it detects a weed, it will spray a herbicide to kill the weed, and then it will move on to the next set of crops. I mean, it will advance in the field. Now imagine if you don't maintain the latency of being able to detect the weed, that weed detection task. If the latency of that task is more than the speed of the tractor, by the time you detect the weed, you actually have gone past the weed and you are going to spray herbicide on actual crops. That will reduce your crop yield, right? So the similar things can happen in manufacturing industry, in automobile industry, where they detect defects in the car body, especially on the paint side. They try to detect using some fixed cameras, and the cars are moving on a conveyor belt. The camera will detect whether there are any defects in the paint or not, and it will try to patch or repaint that particular car. By the time that defect is detected, if you haven't detected the defect in time, the car is going to move in the conveyor belt and go past that detection system. That will cause delay in manufacturing. So latency is extremely important. Second point is reliability. We may have 5G, 6G, whatever G, but at the end of the day, all these communications happen over cellular networks, and cellular network will never be 100% reliable because it is shared among a number of users, n number of users. So when in disaster management or mission critical systems where reliability is an essential need, you need data to be processed right at the source instead of sending it to the cloud over the wireless network. Inherent privacy is another typical requirement, especially for healthcare applications. The first application that I was talking about. You won't want to send all your private health data over open internet to the cloud. That's a violation of privacy. And after this GDPR and all those things have come in, this is a very stringent requirement. So healthcare data, it's always best to process in-house within the premises. So using all the sensors and all other devices, if I can actually do some basic form of computation, at least get some alert, then that alert can be sent over to the provider using open internet. But in that case, my health data, basic health data, my body vitals, those things are not being shared over open internet. So edge systems processing right at the source of the data on the sensors or near the sensors, that ensures this inherent form of privacy. And it also lowers the communication cost, which is actually low cost in the sense of battery consumption. Most of these edge devices are battery powered. So if you try to send data over the internet to the cloud, that communication itself consumes the battery a lot. So you have to try and do this at the source itself to reduce that communication cost. But there are challenges. These devices are smaller. The CPU is small. The memory is not hundreds of gigabytes. Then there are network and power constraints. The low latency, reliability, privacy, and lower communication cost, that kind of rule this area, which is why edge devices are getting more and more popular, trying to process the data, trying to infer right at the source of data or near the source of data. While all these things have been happening, we also started incurring a huge cost because of this intelligence. So if you consider the energy cost of AI, if you think about the large AI models like the Gen AI models, BOT or ChatGPT or whatever, these large NLP kind of models, they emit carbon dioxide, which is equivalent to the lifetime of 5 American cars, starting from the production of the car to the end of life when the car goes to the scrapyard, equivalent to 5 cars. Lifespan of 5 such cars. When GPT-3 was trained, the previous version of GPT, when GPT-3 was trained, they used 45 terabytes of data to train it on 512 NVIDIA V100 GPUs, and the training went on for 9 days. The total energy consumption was 28,000 kilowatt hours. Now, if you compare it with an average American household consumption, that is almost 1/3 of that 28,000 kilowatt hours per year. Whereas GPT-3 consumed 3 times of an average household consumption, annual consumption in just about 9 days. When BERT was trained, the first Gen AI model from Google, when BERT was trained, it had a carbon footprint of roughly 1,400 pounds of carbon dioxide. That was equivalent to a trans-American flight from San Francisco to New York. And if you use neural architecture search, try to build the network from scratch using the data set as the training element, then that entire energy cost is equivalent to a full 747 jet. So that's the cost of energy we are looking at. Now, so in 2021, there was a paper on this growing energy crisis, and it was figured out that if Google just changes their search engine to Gemini, so instead of Google search, if Google allows people to use Gemini for all their searches, then Google AI will start consuming more energy than the entire country of Ireland. And there was a report from the Semiconductor Research Corporation which claimed that by 2050, this global computing industry, the industry that we are talking about, the future of computing, this global computing industry will be processing 10 to the power 42 to 10 to the power 45 bits of data per second. and that will make the energy consumption of the computing industry very close to the global energy production, which is not good actually, which is bad. So why is these things happening? Why is such a severe amount of So why is this kind of energy being consumption happening? So one reason is the complexity of the models, which has increased a number of times, hundreds of times probably. So earlier, can the mics be muted, please? So earlier what we had was algorithms that did or models, AI models that did different kinds of things. So you had sensors. This is an example from robotics. So you had sensors on the robots that sense the location, the position, and all those things. Based on that, the robots would run a perception model to perceive what's around itself. It will try to localize using a localization model. Then using all these things, it will try to do a high level path planning. Then it will do behavior arbitration, perform low level path planning. And then finally, all these things will go to the motion controllers to make the robot move, to navigate along the path it has planned. So that was the earlier form of computation. Nowadays, what we are seeing, and this trend is growing actually. So you have the sensors, you have one model. That model does everything, starting from perception, localization, high level, low level path planning, actuating the motion controllers. Everything is being done by one end-to-end model, and that model tends to adapt to the changing data. We call this kind of model foundation models. That takes multiple sensor inputs, varying type of inputs, and try to process all of them, make sense of the entire thing, the whole data that it's getting from the sensors, and then control the motion controllers. So that's how things are evolving. If you look at the cost of computing from the power of systems point of view, for example, how the flops have changed. So the lower portion of this graph, I don't know if you can see my arrow here, the mouse pointer here. So when we had all these deep learning things coming out, AlexNet or VGG or MobileNet SSD, all those things, when they started coming out, the growth of the number of flop requirement during training was around this line, this gray line. By 2018, when transformers were released, that requirement of flops suddenly shot up considerably. So after the growth, after the evolution of the transformers, the flop requirement for training has been growing by 750 times every 2 years, whereas your Moore's law governs that the hardware capability will grow by only 2 times every 2 years. Same thing happened for memory as well, the memory consumption. Transformers started consuming memory, the memory consumption for transformers started increasing by 410 times every 2 years, where again, the AI hardware memory that is governed by Moore's law is 2 times for every 2 years. So that is how dramatically the entire computing spectrum has changed. And this is not this is kind of skewed based given the trend in the increase of speed and increase of memory in the hardware side. The growth in the requirement of flops and requirement of memory is extremely disproportionate. So these are the things that causes the problems, the energy problems, and all other problems that we are seeing. So what we say is that if you want a sustainable future where you want to use AI for all the inferencing and every damn things, where AI will be everywhere and inside everything, that won't be possible unless you make your AI systems or advanced computing systems more and more sustainable. what are the roadblocks to this low power, achieving the low power computing and achieving sustainable AI? So if you see this graph, and if you think of how computing systems have evolved from 1970s onwards, so we had the processors, the clock speed of the processors in early 70s was pretty low. And then Intel and all other manufacturers, they started increasing the clock speed of the processors. As the clock speed increased, our algorithm started working faster and faster. So that was a kind of a linear scaling that happened till about middle of the first decade of 2000. So nearly 2004, 5 up to that point of time. So if you follow these orange lines, that is how the processor scaling happened based on clock speed. Now, I don't know if you can see this pink shaded bar over here. That is the period, what we call the period where Dennard scaling ended. So Dennard scaling was this idea that if I increase my clock speed, my algorithms will start working faster. So that was the period of Dennard scaling. Dennard scaling effectively ended by the middle of 2000, 2005 to 2008, at some point of time like that. So at that point of time, we started seeing the evolution of multi-core processors, dual core, quad core, and so on. Those processors started evolving. So right now we use 8-core or 16-core processors to do all sorts of things. But now Moore's law started flattening by the middle of 2010s. We saw that the Moore's law that governed the speed and hardware, all those things, that 2 times every 2 years, that started flattening because we reached the physical limit of having a number of transistors on a certain given area. So Global Foundries in 2018 scrapped their 7 nanometer transistor production. So effectively, we have these things, that flattening of Moore's law, Dennard's law, all these things coming as roadblocks to our future plan of having energy efficient computing. One is, of course, Moore's law. Because of and the second most important thing is that we still use computing systems that are von Neumann in nature. So von Neumann systems means you have the CPU, you have the memory. For every bit of processing, you bring that data, every bit of data from the memory to the CPU, do the processing, right back to the memory. Now, when you have this humongous volume of data to be processed for all these AI systems, Gen AI and Google's DeepMind and all these things, when you have this humongous volume of data to be processed, each bit of data has to be brought to the CPU for processing and written back to the memory. That effectively creates a congestion on the memory bus that connects the CPU and the memory. That creates heat. You have to cool the system, so you have to have more electric systems for electrical cooling systems. That raises the requirement of energy. So memory wall, which we call the von Neumann bottleneck, which creates the heat wall due to this von Neumann paradigm. Everything taken together, our energy consumption is kind of on the verge of going out of control. So these are the problems that we see which act as roadblocks to our sustainable future. Now, at the same time, if you think how people do these kind of things, so Gen AI paints a picture or writes an article. IBM's Watson played against a human quiz champion and defeated the person. But we do the same things using just about 20 watts of energy. Whereas when IBM Watson was trained, it was consuming around 85,000 watts of energy, which was enough to light up the entire block of Manhattan in New York. So that is the difference between the processing of computers in terms of energy, thousands and thousands of watts. And we can do the same thing using just about 20 watts. So can we get some inspirations from the brain? That is the future of computing that we are looking at, how we can emulate the way brain performs similar kind of computation. So to begin that, before that, we have to have a 60-second primer on brain. So why do we have brains? Plants don't have brains, and still plants are living organisms. And there are certain small invertebrates under the ocean, sea squirts. These sea squirts are hatched with a very elementary nervous system, and then they swim through the ocean, settles down on a distant rock, and it just eats its own nervous system, eats its own brain. But after that, sea squirts are still alive. So neuroscience says that animals need brain to move, to find food, and to find partners. All these activities that we do can be covered in these things using the sensory motor perspective. So typically, brain produces a goal-directed behavior that will maximize the probability of survival. So that's how brain processes things. Now, what happens in brain? The brain way of computing. So we consider three distinct areas, three distinct points. One is the algorithmic efficiency of the brain. Two is the concept of anticipation and semantics. And three, the concept of adaptive learning and invariant representations. I'll just briefly tell you about each of them. So for example, algorithmic efficiency. So let's take a scene understanding example. This is an image that you probably have recognized already. And it took you maybe 2 to 3 seconds, maybe even less than that, to recognize what this picture is. It's Victoria Memorial in Kolkata, right? So all Kolkatans know this. But if you want a computer system to recognize the building, you'll have that system will have to process few thousand lines of code, and to decide that it's a building, and there is a water body in front of the building where there is a shadow, and then of buildings trying to match this one, trying to find the similarity with other things, and finally it will end up in telling you that okay, it's Victoria Memorial. Whereas in brain, the whole thing happens within 10 to 100 synaptic stages. Humans have not written any algorithm that is more efficient, any artificial algorithm that is more efficient than the way brain handles these kind of input signals, the perception and all these signals. At the same point of time, neuroscience also says that our brain has only one algorithm to process everything. So the idea started coming about in about 30 years ago, when a few neuroscientists in different labs across the world tried a novel experiment. So there's a little animal called ferret, something like a squirrel. So they, in each of these labs, the neuroscientists, they experimented on neonatal ferrets. So the idea of the experiment was, when mammals, us or ferrets or any other animal, when we see something, the signal from the eye travels through the visual, the optic nerve up to the visual cortex, where the processing happens. So our scene understanding and all those things happen in the visual cortex, the zone in the brain which processes signals from the eye. When we hear something, the sounds and all those things travel through the auditory nerve up to the auditory cortex, where hearing is processed. So ideally, we'll think that okay, a person hears via his auditory cortex and sees via the visual cortex. If we mess up with the connection between the nerves, then the person won't be able to see or hear. So the whole thing will be messed up, right? So that is the common idea. Now, what these neuroscientists did was, they disconnected the auditory cortex from the ear. So they just severed the auditory nerve. And in turn, they connected the auditory, they connected the eye with the auditory cortex. So they rewired the optic nerve to the auditory cortex instead of the visual cortex. Now, common perception will say that the neonatal ferrets will never be able to see, eventually they will die. But what happened was, after 3 months or so, the neonatal ferrets started to see. They were being able to see things. So auditory cortex learned to see things. From this, the neuroscientists decided or derived that there is only one algorithm inside the brain, whether it's visual cortex or auditory cortex, doesn't matter. It's the same algorithm that behaves differently given different types of input. So the algorithm running inside the visual cortex, that allows us to see via the signals coming from the eye. The same algorithm, when it runs inside the auditory cortex, allows us to hear things via our ears. The same algorithm, when running on the somatosensory cortex, which can infer touch, can figure out those touch from coming from different parts of our body. But it is the same algorithm. The way deep learning and all AI systems work today is everybody is trying to find that holy grail, that one algorithm. What is that one algorithm which can process different types of data and differently and end up inferring the correct things? So that is the algorithmic efficiency part of the brain. Second is the anticipatory part of the brain. Brain happens as an anticipatory system. So think like this. So you go every night, you go to your bed and you sleep, and next morning you wake up, you move your feet down to the floor, and then you stand up. You know where the floor lies. You have anticipated the floor every time from your childhood, that this lies maybe at 2 feet distance from your bed. Now imagine in the middle of the night, I go inside your room and lower the floor by 6 inches. In the morning, when you wake up, you'll still anticipate that the floor will be at 2 feet distance from your bed, but it's actually 2.5 feet now. So you'll just, tumble over and fall on the floor because your anticipation has gone wrong. When we talk, we anticipate our future words, the next words. And when we talk, we go back to previous concepts. When we talk or when we read or when we write, all our concepts that we have learned from our childhood, all these things, we go back to each of them. So when we are reading something, our concepts link to dictionaries inside our brain that tells us the meaning of words. Then that same dictionary kind of area inside the brain relates to the area where alphabets are stored, because you can only figure out a word if you know alphabets. So all these things are connected in a kind of a map, in like a flow graph. You go back to previous learnings and learnings even before that. So all your experience from your childhood matters to what you do at some point of time. And then there is a semantic map inside our brain. Languages every language almost have different meanings for the same word in many cases. Let's take the example of hot in English. So hot might mean hot weather. It might also mean hot food, that is in terms of temperature, food where the temperature of the food is high, like hot tea or hot coffee. It might also mean hot in terms of spicy. So Spanish food or Indian food, the spicy foods, they are also hot. Hot in terms of people who are very smart and all those things, they are also hot. So each of these hot words are stored in different areas of the brain. And we are seamlessly able to relate to that area, to connect to that particular area inside that brain, inside that semantic map, based on the context of the whole thing. So if we are talking about hot food, somehow our brain seamlessly connects to that particular area inside the semantic map where temperature related hot or spicy related hot is stored, not any other hot. So that is how brain keeps a semantic map and uses it when we talk or write or read. Lastly, the invariant representation. This is one of the most critical parts inside the brain. Everything we see, hear, or remember, everything is stored inside the brain in an invariant way, because of which whether it's night or day, whether it's raining or snowing, we can still recognize that, okay, this is the Victoria Memorial, because the image of Victoria Memorial inside our brain has been stored irrespective of the weather conditions, irrespective of the lighting conditions, irrespective of any other environmental conditions, which doesn't happen in case of computers. So if you show the image of Victoria Memorial, or in this case the image of Vishwa Bangla Gate when it's snowing or the weather is too bad or it's too foggy, the computer is going to have a hard time to actually figure out what that image is, because it never has gone through this invariant representation, and we don't actually know what is meant by this invariant representation in terms of brain. How does brain store this kind of invariant representation? The last point inside brain is synaptic plasticity. So as we see things, hear things, learn new things, it creates a circuit inside the brain. For everything that we see, hear, touch, feel, there is a circuit. So for the first time you see a red cup, some nerves inside the brain joined together to create a circuit to tell you that, okay, this is a red cup placed on the right hand side of the table. When you see that red cup again placed at the same place, same nerves are activated, same neurons are activated, and the circuit becomes stronger. The bonds become stronger between the neurons. This idea in Hebbian learning terms is called that neurons that fire together, wire together. So the neurons which get activated because of something you were doing, some activity, maybe it's perception, maybe it's reading, writing, doing something. The neurons that get activated during that activity will wire together, form a circuit. Every time you perform the same activity again, the same neurons will fire again, same neurons will get activated again. This is synaptic plasticity, how memory is stored inside our brains. So even if we sleep, our neurons are not really active at that point of time, but when we wake up, because they have formed a circuit already, we can still perform the same activities over and over again, because neurons are now wired. So there are certain facets of biological intelligence and computational intelligence which makes these two things different. Biological intelligence is very good in visual comprehension, audio and speech comprehension, navigation, route planning, decision making, and we can do all these things from very limited amount of data. Think about yourself when you first learn to distinguish between cats and dogs. Your parents probably have showed you only 5-10 cats and dogs. You learn to distinguish between cats and dogs from very high level features, differences between them. Google, when it started recognizing cats and dogs, it was shown probably few 100,000 images of cats and dogs. Even then, it was not perfect, right? So we can learn, we can do all these things very efficiently with very low energy consumption, and we can learn all these things from very limited amount of data, which the computers cannot. Even today's computers, the most up-to-date advanced computers cannot. But the computers are good in the computation, the processing part. It's very fast. They're very fast. The speed, very high speed. They can access the memory very fast. The lifetime is great. The memory capacity is great. The accuracy is great. But all those things kind of get become less important when we see what humans can do, and they can do it do it more adaptively. Perception, adaptation, flexibility, cognition, learning, innovation. You give certain things to a robot, which may be very intelligent robot, very much trained with all those things. A robot, it will only do the things that it has been taught to. It won't be able to do something new from all those things that it has received, whereas a human will be able to do something new, create something new. That is the difference between biological intelligence and machine intelligence. There is also another attribute inside the brain. I'm talking about the brain over and over because I'll take you to neuromorphic, which is one of the advanced computing areas where all these concepts are actually embedded. So data sparsity inside the brain. I told you that we can learn from very limited amount of data, like 5 cats and dogs when we learn to distinguish between cats and dogs. And brain stores an invariant representation. So this is probably one rendering of that thing which people did, which Carver Mead and his student Misha Mahwald, they did in 1991. They created a silicon retina. Electronic version of human retina, and this image that you see is actually the image of a cat in a way that we actually see inside the brain. We don't know that we see a cat in this fashion, but this is actually the image of a cat that gets registered inside our brain at our visual cortex. So this silicon retina has now been modernized to create a dynamic vision sensor, DVS camera. And if you see the image on the right hand side, that is actually how things happen. So there is a family, a father, his daughter, and a dog. The DVS camera is actually only recording the pixels where there a change of luminosity has happened. It doesn't record the full frame. That is the efficiency of the brain, and hence the same thing has been replicated in DVS camera. It doesn't have to record the entire frame pixel by pixel. It only records those pixels where a change in luminosity has happened at a given point of time. So there is a spatial dimension, there is a temporal dimension. At time t, some pixels had a change of luminosity, that thing is recorded, which is why you see only that outline or some parts of the interior of the bodies of these three figures where the luminosity has changed. That has been recorded by the DVS camera. When we talk about neuromorphic systems and stuff, this is the kind of things that we do. These are the type of data that we try to process. One last functionality of the brain is some form of inherent mapping inside the brain. Our brain has certain cells which can act as an inherent GPS. We don't need Google Maps inside map ourselves inside a given locality. This was actually proved by John O'Keefe back in 1974, where when he detected inside this, if you see the video, if you note the video inside this experiment, where he probed the brain, certain neurons of a rat and placed the rat in a black box, and then he recorded the movement of the rat. What you noticed was, whenever the rat was crossing through a place that where it has been before, the same neuron was getting activated. Right. So see, the rat is moving inside the brain, and when it's crossing a given place, a certain neuron is getting activated, and it was finally reduced after the end of the experiment. It was reduced that the same neurons actually activated when the rat was retracing the places that it has gone before. The same neuron was getting activated over and over and over. So John O'Keefe discovered this specific type of neuron that gets activated when you go back to a place where you have been previously. The neurons let you know that this is a place that you are revisiting. You have come here before, and because of it's related to place, O'Keefe named these cells place cells, PLACE, place. So these cells are the place cells inside our brain. Around 30 years after that, Maybrit Moser and Edward Moser, two students of John O'Keefe, they extended this experiment, and they pointed out that if you see the if you see the data at the end of the experiment, you'll see all these dense areas where the neurons have fired together, those areas kind of appear like hexagons or triangles. So eventually they deduced that using these special place cells, you actually have a spatial grid inside the brain, which is why when you stand in a room or in a given space, you can localize yourself very efficiently with respect to that space. Inside a room, inside a library, inside a stadium, you are very efficient in localizing yourself inside that particular given space, just because of this spatial grid that is already there inside your brain. So the Moser couple named these type of cells the grid cells, and jointly, John O'Keefe and the Moser couple, they won the Nobel Prize in biology in 2014, I think. So it took 30 years to discover the next step from the place cells that John O'Keefe discovered in 1974. So together they also found some other special neurons. Few other neuroscientists also combined there. So border cells, when you start standing or sitting at the edge of something. So when you stand at the edge of a mountain or a hill station, you have that feeling of nausea because some border cells inside your brain, they got activated and told you that you are standing at the edge of something. Head direction cells tell you which direction you are going, east or west. Speed cells tell you that at what speed you are going, at least an approximate speed. Speed, their firing rate increases proportionally with the speed. So when you move faster, the speed cells start firing faster. So all these concepts, as I told you, that we are trying to use these concepts, the concepts from biological intelligence, to do something in the area of computing. So all these concepts, the concepts of place cell, grid cells, border cell, speed cells, they were used by Google DeepMind to create an agent system that was able to navigate in different cities only using the Google Street View camera or landmarks, not the actual Google map. So that's actually how we navigate. If we don't have a map, we know the place, we know the landmarks, we can see the landmark. Based on the landmark, we walk on a road, turn left or right, and then navigate, and then actually end up going close to that landmark. That's how we have navigated always when we didn't have Google Maps. So Google's DeepMind trained one such computational agent using the Google Street View camera, the view of houses, structures, and other things in cities that come at the on the side of the map. If you just drop that little person on the Google map on the street, you'll be able to see these images. So based on these images, the system was trained. It was trained in New York, and then the same system was able to navigate in London, navigate in Paris, navigate in Moscow, just like a human will be able to do. If he knows the basics of navigation, he will be able to locate and navigate himself or herself at unknown places. So we have talked about edge computing systems that reduces the energy cost of data movement, and we have also talked about the biological intelligence, and our goal is to figure out whether we can replicate this mammal-like biological intelligence, efficiency of biological intelligence at the edge and also in the cloud. Can we make our computing systems more like biological intelligence in terms of energy consumption? So what we have already seen is that the von Neumann systems consume more power. Neuromorphic systems, and now I go into my specific area. Neuromorphic systems are a new type of evolving computational paradigm which co-locate the computation and memory uh, just like mammalian brains. So just like your neurons and synapses are co-located inside your brain, the neuromorphic system, the neuromorphic processors, the architecture of the processor is pretty much similar to mammalian brains in terms of the computational entity, which is a neuron, and the synapse, which is the temporary storage. They are connected together on the same processor. And we use a different paradigm of computing called the spiking neural network paradigm, which is often called the third generation of neural networks. And this is known to have, this has shown that it can reduce the energy consumption by up to 1,000 times. So what is this spiking neural network and why do we use it? So before that, you need to understand the story of spikes. Why does spikes happen, and what are they actually? So spikes are basically electrical signals that happen inside our brain during any kind of stimulation that the brain receives. It can be seeing something, it can be hearing something. So like when I'm talking, you are listening to me, and every time you listen a note or a sound or something, some spikes are happening inside your brain, because of which you are able to understand hopefully what I am saying. So how do these spikes happen? It's because every neuron, if you see the leftmost picture, that's an image of the cross section of a neuron. So there is a fluid inside the neuron, and there is also there is a fluid outside the neuron. Inside the neurons, there is a high concentration of potassium ions, and outside the neurons there is a high concentration of sodium ions. When an electrical impulse arrives, that is when you see something, hear something, an electrical impulse arrives at the start of at the head of the neuron, which activates this neuron in the sense that that electrical impulse causes a disturbance within these ions, these sodium and potassium ions, because that electrical signal gets converted into kinetic energy of these ions. The ions start jumping around up and down, and more and more sodium ions start coming outside the neuron, and more potassium ions start going inside the neuron. All neurons are typically at a rest state, at an equilibrium state. When this electrical signal arrives and this kinetic energy causes this disturbance in the ions, and the ions start moving around, the electrical potential changes. And when this potential reaches a threshold or crosses a threshold, the neuron spikes. That spike goes over to the following neuron, the neuron that is connected to this one. Same things happen this exactly the same thing happen over there again, and it goes on till that electrical signal reaches your brain. So everything we do, say, hear, feel is the result of a spike. So our brain has around 86 billion neurons, out of which 17 billion neurons are inside the cortex. That is the area where all your senses happen. Senses are inferred within the cortex. And on an average, each of these cortical neurons, they send at most one spike every second. Now, if you take the average life expectancy of any person based on UN data, it's around 70 years. So that 70 years means that you have a lifespan of 2 billion seconds. In terms of spikes, it is 17 billion spikes per second. So your lifespan in terms of spike is 34 billion cortical spike, starting from your birth to everything you have done in your life up till you reach your final stage, that is up, I mean, die actually. Up to that point of time, everything that has happened, everything that you have done, felt, read, wrote, saw, or everything that you have done is the result of these spikes. So as I said, that the neuromorphic systems take up less energy. Why is that? Because one thing, spikes are sparse in time. So if you look at these two videos running over there, you'll see that the spikes happen only at a limited time, only after a certain interval. The spikes happen, then everything goes back to normal, then again a spike happens. So spikes are actually sparse in time. It doesn't happen continuously. It happens, then there is a relaxation phase, then again a spike happens. So effectively, the amount of data that is being processed at your cortex from your sensory organs is very less compared to that real image that we think we see. So instead of having the pixel values for every pixel, only the pixels where the change in luminosity has happened, that is sent to the brain. That is the sparsity which you can infer from these two videos. So these chips, the neuromorphic processors, they are designed to function like mammalian brains. They operate on sparse computation and memory within neurons and synapses. And the energy consumption, as I said, is up to 1,000 times less than compared to conventional systems. So they have the ability to process sparse data. That is one. And the second, they are non-von Neumann systems, basically collocates the computation and the memory. These two things taken together reduces the entire energy consumption of these neuromorphic systems. So this is somewhat a spike looks like, the GIF on the left hand side. And the middle picture where you see the lines, the vertical lines, that is called a spike train. So your sensory organs actually send a spike train like this, where spikes have happened at given point of time. And this timing is crucial. Your brain actually processes the timing information. The spikes are always, they are binary. It's either there or not. So it's 1 or 0. But the timing of each of the spikes, that is critical to the brain to process what has happened. And on the right hand side, you are actually seeing the output of a real DVS camera. So a person is sitting in front of a camera and moving his hand, and you are only seeing those pixels where there a change of luminosity has happened. This is what your brain is actually seeing when you see a person sitting in front of you and move his or her hand. This is what happens inside your brain. So I'm not getting into the programming details of neuromorphic, SNN and all those things. Just to give you a high-level idea, so there are certain neuromorphic platforms which are under research. BrainChip, a Silicon Valley company, a startup, they were the first to bring out one neuromorphic chip up in the market that is called Akida. Intel, one of the tech giants who are also working in this field, they have introduced the world's largest neuromorphic research system, which is called HalaPoint. The Intel's processor's name is Loihi. Loihi had a version 1, now it's Loihi 2. Synsense is another startup in Switzerland who have two neuromorphic processors, SPEC and Xylo. Xylo is meant for auditory processing and SPEC is meant for visual processing or time series processing. There are certain research projects from where the whole thing advanced actually. So these were part of the human brain project. Spinnaker was the first large neuromorphic supercomputer that was designed at University of Manchester as part of the human brain project. Brainscale S was the analog version of Spinnaker, analog version of a neuromorphic computer designed at University of Heidelberg, part of the same human brain project. Other than that, there's another startup called Inatera who have a processor called T, which also performs the functions like neuromorphic systems. There are smaller companies, Spikey from Heidelberg, Prophecy, Zeroth is supposed to be the Qualcomm version of neuromorphic processor, although Qualcomm is kind of silent about this. Synapse is there from HRL Labs. BlueMind is a company. They have this analog version of a very small chip that does time series processing. And Kaspersky, your antivirus company, they are also working on a system called AltAI, again, a neuromorphic system. So what is neuromorphic system? I mean, how is it different from normal computing systems? If you take a look at the Venn diagram like thing on the left hand side, so there is one machine learning concept, or traditional machine learning, statistical machine learning, and all those decision trees and all those things that we do. There is a machine learning. We have been doing these for years. Then you have the neuroscience-driven concepts like neural networks and deep learning. All these were philosophically driven by neuroscience, right? So you have machine learning on one hand, you have neuroscience-driven concepts on the other hand. And then you have the third set of competitive computer architectures like non-von Neumann systems. The neuromorphic systems sit right at the center of the intersection point of all these three sets. So it's a machine learning system which borrows heavily from neuroscience, and it's a competitive computational architecture. So you have these 1, 2, 3 areas where neuromorphic systems process best. So you can have all your deep learning systems converted to neuromorphic. So there are ways to convert ANNs and CNNs into SNNs. So converting an ANN that does something into SNN, and you can use these deep rate coded deep SNNs there. There are ways to approximate back propagation of SNN, because now probably you have understood that spikes, that's just a spike at a given point of time, and back propagation works on doing a derivative of the error on the error. Now spikes, how do you do a derivative on a spike? Because spike it's just a spike, right? So it's at a given point of time. You cannot do differentiation of a spike. So you have to approximate how back propagation works in SNN. Those things are being worked upon in some area. Then people who work on brain, people who try to simulate the brain, people who try to use different neuroscience concepts to figure out how our limbs like hands and feet work, and especially people who are working on Parkinson's and all those things, they try to use neuromorphic systems. Also in large scale optimization problems, one of the properties of neuromorphic systems is that they can reach the near optimal solution pretty quickly, much faster than deep learning systems. So if you have a large scale optimization problem like traveling salesman or any CSPs or any kind of vehicle routing problems, things like lasso on all or graph search, all these things, it's understood that neuromorphic systems will take you to a near optimal solution very quickly. From then you can perform few more steps to reach the final optimal solution. That is one thread of work that is going on. And the last one is different types of physical things like localization and mapping in robotics, olfaction in inspired rapid learning. How do you smell artificially? Say in case of mines, if you want to smell whether there is a poisonous gas leak without having a person over there, you just have an AI system that is able to smell and figure out that there is a poisonous gas leak. So all these things are happening at the same time in the third thread, which are closer to the industry. So this is an example, the benchmark from using a keyword spotting example. That is one of the most common examples that people tend to use. Hey Siri or OK Google, things like those. So people perform the same experiment on a CPU, on a GPU, on a Jetson, I think Jetson Nano or Jetson TX2 probably, on a Movidius in neural compute stick and on Loihi. And the charts over there show the power consumption of each of these systems, and the lowest power consumption you can see clearly from the graph is that of Loihi, and the highest is that of GPU. And if you take an inverse of this, translate that to efficiency, then this tiny circle over here is the efficiency of a GPU, and this largest purple circle over here is the efficiency, the energy efficiency of a Loihi system, which is a neuromorphic system. So basically they require very low latency real-time processing of input. They can benefit considerably from high energy efficiency, and has numerous other practical applications for kind of industry that can be adapted to the industry. Well, what we do at TCS, first thing is, why do we use neuromorphic? Because there is a huge need of low power processing, sustainability from the business lines that TCS has, and because neuromorphic systems co-locate computation and memory, we can expect to reach a huge amount of energy efficiency and sustainability things. On our side, we have been working with this for the past 4 years or so, starting late 2019. And we have worked on different applications like gesture, action recognition, time series processing, classification, prediction, and image segmentation, classification, data compression, lossless data compression. We work on different types of platform tools. We have worked on different types of algorithms, feed forward, recurrent, reservoir, spiking, QA, and different types of learning algorithms. So on the hardware side, we have this brain chip Akida system with us. We are tied with Intel, so we can try to use their simulator. We don't have the chip yet, but we are trying to get one. We are trying to procure Synsense as well. So, and we have a running project with IIT Delhi, where we are trying to create our own in-memory computational system that will work for certain types of signals. So that's where we stand. Globally 7th in terms of IP, and the only large commercial organization in India who is working in this space. We have over 18 publications at top tier venues as well. So these are the kinds of examples that we have been doing. This is what we did. This is what our first venture into neuromorphic. The left hand side, the GIF that you are seeing. That was our first work on neuromorphic systems, jointly done with BrainChip, and this was demoed at NeurIPS. So here the idea was, a person will perform some gestures in front of a DVS camera. A robot will understand or infer what that gesture is. I mean, a neuromorphic SNN network will actually derive what that gesture means, and based on that, a robot will perform some action. So you're seeing one of my colleagues sitting over there in front of the DVS camera. When he's making the gesture, the only input that the DVS is getting is that just outline of the finger or outline of the hand. That is translated to a command which is sent to the robot, and the robot moves forward or turns backward or turns sideways. Those are the things that it does. So what we achieved was the whole system was able to learn new gestures in real time within 3 to 5 seconds. So you teach it, say, 4 gestures, and then you teach it and then start working on that. Then at some point of time, you decide that, okay, I want to teach a new gesture. You perform that within 3 to 5 seconds. It will learn the gesture real time on chip online. And the energy consumption that we achieved was for each gesture processing, each frame processing, 200,000 events were processed, and that energy consumption was less than 3 milliwatt. We extended this work to the IBM DVS gesture data set. So for the application was human-robot collaboration in manufacturing, retail, or hospitality kind of industries. So we were able to achieve a top 3 accuracy of 95% with a very high energy efficiency. And then we tried to do a different thing for elderly care, where I talked about elderly care in the beginning. So that's a very preferred application in our lab. So as I said, the elderly people they don't like cameras inside their homes, right? So because cameras can see people. Now, if I can put a microdoppler radar outside their home, there are no images being captured, but the radar can detect movements. So if you perform any kind of action, the radar can detect that. And we tried the same thing, the same neuromorphic approach on radar data, and the accuracy was at par with any state-of-the-art machine learning approach. We had a paper at IJCN in 2020 on this, and the energy efficiency was also great for this. Then we extended this to visually impaired people. So with a very cheap microphone array, if you perform air writing in front of the microphone array will capture the sound of the movement of your hand and fingers. And then we were able to detect gestures and air writing, like you write something in air in front of the microphone array. We were able to decipher what that gesture was and what that air writing letters were. So this was all these things are part of that neuromorphic action gesture recognition spectrum. We are trying to work for medical data as well, and neuromorphic specially fits this medtech industry because of the special features, like it has the capacity of very early pattern recognition, it has very low latency, it is fault tolerant because neurons are actually parallel, they are parallel systems. There is sparse connectivity, hence less data. It is adaptive, it can learn on the fly, on the job, in real time. It can perform parallel processing, the energy efficiency is high, there is real-time processing. All these conform to the requirement in the medtech industry. For example, understanding of ECG or EEG signals. And more importantly, what we are seeing now is there is a requirement of rate-responsive cardiac coding. Say one pacemaker, the pacemakers that we have today, they are fixed rate, right? So irrespective of your activity, the pacemaker will send a signal that will try to that will activate your heart. So it might send us it will send the signal for your heart to beat faster or things like those. But say you are doing some activity, you are walking up the stairs, so your heart is already beating faster. You don't need a signal at that point of time to make your heart beat even faster, right? So your pacemaker should actually be adaptive to the activity that you are doing. Based on that, it should change the signal, change the frequency or intensity of the signal to your heart, so that your heart can adapt itself to the activity that you are doing. Now, this is called rate responsive cardiac coding. If you want to do this on a pacemaker, it will actually be eating up the battery of the pacemaker. You cannot send the whole thing to the cloud, right? That doesn't make sense. You have to send everything, every signal to the cloud to make the decision in the cloud. You have to do it at the edge on the pacemaker itself. But if you start doing this thing on the current pacemakers, the pacemakers of today, will, instead of having a lifetime of 7 to 10 years, the pacemakers will end up consuming the entire battery in 3-4 years. So the device lifetime will be less. Now, to change the battery of a pacemaker, you need to go for surgery. Every surgery increases the chance of infection by 10%. So this thing, a headache, is a headache for medtech providers, for healthcare providers, for hospitals, for insurers, and of course the patient. So that's why neuromorphic is thought to be one of the most fitting solutions for this rate responsive cardiac coding, which is one of the targets that we have. We already have worked on analyzing ECG data, and we have tried 5 well-known data set and achieved over 95% accuracy, which is quite good actually in this area. One of the most important applications that we have been doing has been in the satellite space. Since this opening up of the satellite, the space industry, people are now sending lots and lots of satellites for doing multiple things. Even corporates are launching satellites. So you can do Earth observation like monitoring of forest fires, monitoring of ocean liners using these satellites. And specifically, these satellites are often small. The ones that you see on the image over here is called a CubeSat. A CubeSat is the smallest CubeSat is the size of a Rubik's Cube, 10 centimeter cube on each side, size of a tissue box actually. So you can imagine that these satellites don't have enough space to take a solar panels. So they are very much energy constrained and also processing constrained, computationally constrained. And they're also constrained in terms of the time window, which is allowed for communication with the ground station. These move in the low Earth orbit, 500 kilometers. So it's just about 12 to 15 minutes time window that it has to communicate with the ground station. So what we did was we statistically we saw that the images that are taken by these satellites, 50% of the images are cloudy. Now, current satellites, they downstream all the images to the ground station, and 50% of half of those images are actually not usable because they are cloudy. Now, effectively, the satellite is eating up its battery by sending unusable things. So we decided that can we do something on board so that only the images that are usable, those will be sent, rest will be rejected. So we tried that. We created a spiking neural network on this Akida, brain chip Akida, and that was able to detect and classify images, cloudy images from non-cloudy images. And it saved us around 35 to 230 times energy compared to a Jetson TX2, and it was also 3 to 7 times faster than Jetson TX2. And after this reduction of images, rejecting the cloudy images at source, we performed lossless compression on the images, and we achieved up to 50%. And we achieved up to 50% compression, and at the same time consuming very low energy, and the compression was even lower in terms of energy consumption than 7Z. So this was benchmarked along with ESA and BrainChip on ESA's special data sets presented to ESA at the Movidius conference, and next year probably we hope sorry, no, not next year, actually this year at some point of time, this algorithm will be in space on a brain chip Akida hardware on a ESA launch satellite. So that is one of our targets this year. So finally, the startup thing. I was kind of confused on how to relate the whole thing with startups. But what I know is that almost all the new hardwares that came around in neuromorphic are from startups. So brain chip Akida, that's a startup. Other than Intel, Synsense, Inatera, all are startups. In fact, in India, The only Indian company, not company, it's a startup from an academic institution. From IIT Bombay, Professor Udayan Ganguly created a startup, and they have the India's first neuromorphic chip called Numelo. So startups have already started playing a big role in creating these neuromorphic chips, Brain Chip, Synsense, Inatera, this academic startup from IIT Bombay. The problem is, as I said in the beginning, that there are diversity amongst the hardware. In case of neuromorphic, there is no standardization at all. So you create a model for brain chip Akida, you cannot run the same model on Intel. Right. So there can be an area for startups where you can look at developing open, modular, and scalable hardware platforms based on some open standards. You can create standardized interfaces or middlewares that will enable this interoperability and portability. There are many unsolved problems in neuromorphic in both software and hardware. You need innovative training paradigms. Okay, I'll just end it here because everybody is probably impatient. So let's take the questions.
We are extremely sorry. I think one participant who has unmuted. Mr. Shubham Roy, you are unmuted. Please mute yourself.
Hello. Hello. Hello, sir. Hello, sir.
Yeah. Yes, sir. You are audible, sir.
No, I am audible. I know, but there are others audible as well.
No, actually, so Dr. Shubham Das, you are audible. Sir,
Yes, sorry. Extremely sorry for that, but we are having a very interesting session. Can you please, sir, continue it?
Yeah, okay. So this is the last slide, so I won't stop you for long. So there are many unsolved, as I was saying, that there are many unsolved problems in neuromorphic, both in software and hardware. So you need innovative training methods for SNN. As I said, the backpropagation is an approximation that we perform here. So can we do something more? Can we have some more type of unsupervised learning algorithms in neuromorphic? Can we create hybrid models that will combine traditional AI and neuromorphic approaches for diverse applications? For example, as I said, neuromorphic appears to a near optimal solution very quickly. So if you can use a neuromorphic system in tandem with a perfect AI system of following deep learning, you get a near optimal solution, then operate on that, and then get the actual accurate solution that will also happen quickly with less energy consumption. There is ongoing research on the materials for synaptic plasticity because, as I said, brain has a default synaptic plasticity. You sleep, but you still remember things. Neuromorphic systems or any other computational system, you switch that off, it will forget everything. Then you have to start from scratch. So people are working on memristors, phase change memory, on NV non-volatile memory modules, spintronics, trying to figure out which is the best material to create neuromorphic systems so that you can achieve this synaptic plasticity. That's another area for startups. All the companies I know, other than academics and other than Intel, are basically startups. So you can focus on optimization of energy efficiency with large-scale neuromorphic systems, develop adaptive hardware, create new learning paradigms for neuromorphic systems. We only have that STDP as a current learning paradigm. So what else can we do? What are the other areas, the emerging fields where neuromorphic could excel? We know about robotics, we know about healthcare, we know about smart wearables, but other than that, where else can we use these brain computer interfaces? Where else can we use these decentralized AI and achieve something good to some form of sustainable AI? So you can try to innovate new use cases for space exploration, environmental sensing and monitoring, disaster response. These are all areas that you can work as a startup And as I say, almost every company other than Intel and the academic institutes that I know are actually startups. So there is a huge startup play in neuromorphic, especially India semiconductor mission, and all those things are there. So maybe something can be tagged with that, and then you can start working on this. So that's all. Thank you.
So, sir, please.
Yes. Hello. Hello.
Yes, sir. You are audible, sir.
Hello, sir.
You are audible, sir.
Yes,
Okay.
yes.
Yeah, sir. Sir, thank you, sir. Dr. Arijit Mukherjee, scientist of TCS Research. Sir, actually, this one is also a very interesting topic for me, because a few minutes back you have discussed about how we are using this technology in robotics. Basically, I'm interested in robotics. My research area was also robotics. Um, so how brain chip, data consulting services are jointly working in the field of robotics, how it is working. Uh, so this really attracts me. Actually, I don't know how much it is attracting the others. I hope everybody, all of us, must have gained a lot of information from you. And more or less, what I can say, that nowadays the future is actually the future research is actually here. What I can say in the neuromorphic computation. So thank you, sir, once more. Is there any question anybody want to ask?
I have
From anyone?
Am I audible?
Yes.
Okay, sir.
Yes.
It was a great talk. I have one confusion. In one of your slides, you have mentioned that some radar signal that you record from the gesture of the hands.
Yeah, so it's a microdoppler radar that we used.
Yes.
I'll show you.
So how you can record the signal? What kind of microphone or device you have used?
Oh, that's the I mean, this one, right?
Sir, at the
This
screenshot,
one.
192.
This one. Yeah. So I don't know about the recording from my side, because we work closely with the sensing team. They created this radar, and they took images of these middle things that you see. Those are the signals that they recorded, and we worked with them to create the neuromorphic system. So I'm not a radar person, so I cannot tell you how these signals can be recorded. That's sorry, but
Okay.
it's not my
Okay.
area. I know what happened after that. The
I don't
processing
think
part
the
I can
radar
tell you.
part is visible right now.
Okay, sir. Thank you. Thank you very much, sir.
Oh, did I stop sharing?
No, it is there. Yes. Okay, sir.
No, the
Yeah,
radar
this
part was not visible.
Yeah, now it is visible, that part.
Yes, right now it is visible.
Yeah.
Okay, sir. Thank you.
Okay.
Dr. Mukherjee, thank you very much.
Yes, sir. Also, you shared the idea. You shared the idea that how the startup are also working, and it is also giving us some useful information regarding regarding the works going on in Intel or in startup. And also, it is a great news that TCS is also working here, and the great research is going on. Sir Jubashi sir, do you want to say something?
I have a question. Just in one of the slides you have mentioned that while we were you were showing a photograph of say planetarium, or then you told that the human can easily identify whether that is foggy or something. So the images are being stored identical. But in the case of computer, whenever we are going to process it, it is actually very difficult for the computer. So from there, a question came in my mind. So do you think that for like sustainable computation, do we need to process the data differently so that, or do we need to store the data differently so that computer also can easily identify as human can?
It's a possible idea. I mean, but first you have to know how that, we still don't know what that invariant representation is. I mean, not fully. We have some ideas here and there. I mean, the neuroscientists have some ideas here and there, but it's not foolproof, and nobody is confident about these things. We know very little about the brain. But this is true. If we can teach our computer to process and store data in these forms, invariant forms, then you won't ever need to store an image with every pixel information or store a video with every pixel information for computers to be able to process. But unfortunately, we don't know what happens inside the brain much, so we cannot tell.
Just can I like add a line as a comment as a researcher here? Like I think whenever human identify any image, so suppose if I'm getting an image in a foggy atmosphere or environment, I use my perception to identify. So whenever somebody is seeing, say suppose that Vishwamangla gate, if during foggy also, if I can see say 20% of that, I use my intuition as a human to recognize it.
Yes. So basically, we do a we humans perform an inherent multi-sensor fusion and combine it with the contextual knowledge and experience in real time. No computer can do that as of now. I mean, Gen AI is trying, but there is still.
Thank you. Thank you. Mr. Over to you.
Okay, thank you, sir. Thank you, sir. We are grateful. Also, we are grateful to our digital media partner, the Telegraph Online Edugraph, for associating with us. I hope there is no more question. So,
sir, actually, I have a question.
We should end the session here right now.
So, I have a question.
Okay,
I'm
okay.
Monisha Ghosh from SKFJ.
Yes, please.
Sir, actually, I'm asking about if in this slide, you told that one programmable devices or one algorithm is applicable for our brain to understand the difference between various sensor organs. So, sir,
That is the hypothesis.
Okay. So, sir, can you please tell us that which that SNN model is more applicable for this purpose?
Nobody knows yet. People are, as I said, that neuroscientists say that it's one algorithm that works in the brain. So people are still trying to find out what their algorithm is. Is it CNN? Is it LSTM? Is it autoencoders? We don't know. People are trying different things. Same thing happens on the spiking neural network side. All we know is in the spiking neural network, at least the learning paradigm, unlike CNN, LSTM, STDP, unlike CNN, LSTM autoencoders, one mammal-like learning paradigm is used that is called STDP, Spike Transfer Dependency Protocol, right? Spike Time Dependency Protocol. As I said, mammals process spatial and temporal signals together. So that same thing happens in spike time dependency protocol. You are trying to process the spatial and the temporal signals together. This is the main reason why neuromorphic works exceptionally well for any data that has a temporal dimension, which cannot be handled by normal deep learning systems, but handled exceptionally well by neuromorphic systems, spiking neural networks, any data that has a temporal dimension. like visual data, auditory data, olfaction data. They all have a time signature.
Okay, sir.
Yeah.
Okay. Okay. Thank you, sir. Sir, if
Yes.
we have any queries in future, so sir, can we mail you?
Just you can mail me. This is the mail ID.
Yeah. Okay. Okay. Thank you, sir.
Yeah. Thank you.
Okay, so thank you, sir.
Yeah.
We should end the session right now.
Okay.
I hope
Thank you.
there is no more question. Thank you
Yeah.
very much, sir.
Any question? Feel free to email me. Thanks. Bye.
Sir, one thing, can we get this as a note from your end? Is it possible? I hope sir is not present here. Okay, thank you.
Okay, thank you, Dr. Arijit Mukherjee, and for the nice session, and Dr. Shobhit Kumar Das for the moderation of the session. As we are running behind the schedule, without any further delay, I invite Professor Siddharth Bhattacharya to moderate the next session. Professor Siddharth Bhattacharya, please.